Okay, well, good evening, everybody. I'm Steve, W4YHD. Home QTH is Fairfax Station, Virginia. That's about 16 miles west of Washington, D.C. And I was the chief engineer, chief designer, and hands-on engineering manager for the HAARP project for 18 years. And I still remain since 2013, I guess it was, as the part-time chief engineer for HAARP and very much involved with the project. So I want to give you a talk on HAARP. This is sort of a engineer's view, and it will emphasize areas of interest to amateur radio operators. Just some quick background on me. I became a licensed radio amateur at the age of 12 years old and have been continuously active in HF, DXing, digital modes, FM and repeaters. All these years, I'm a life member of the ARRL and life member of QCWA. And I've been continuously active. Can't imagine my life without amateur radio, and it positioned me for a great career in electrical engineering. And doesn't it just figure that a ham would be in charge of the design, build, and operation at HAARP? And that is certainly the case here. And we're going to tell you that story. Educational background, Bachelor of Science in Electrical Engineering from Virginia Tech down in Southwest Virginia. And then later on, I went to the Johns Hopkins University, got a master's degree in electrical engineering with emphasis in radar systems engineering and also RF and microwave engineering, effectively a double major there. Okay, let's talk about HAARP. This is about a 50 to 55-minute presentation. I'd like to hold all questions till the end of the talk to get through it, and then we can have a Q&A after the presentation. So HAARP was actually designed by a very small team of folks. We had contractors to assist us at times in building it, but here's a list of the principals involved. And again, I was the chief RF design engineer in charge of all hardware systems except for the power plant. But everything else, diagnostics, networking, RF, you name it, I was in charge of it all. And it was the biggest challenge of a lifetime. And we're going to tell you that story. Okay, so what is the current status of HAARP? Well, the site construction was completed in 2007 for full power operations. That's for our biggest instrument at the site, which is the big HF transmitting phased array, which we'll be talking about in detail. It's a 42-acre phased array, so unique in its design and build. Total input power, 3.6 megawatts of raw RF, and effective radiated power at the high end of our band, which is 10 megahertz. I'll explain why that is. It tops out at 5 gigawatts. And we completed that initial first build out and passed all acceptance tests in 2007. The program and site, unfortunately, were shut down in June 2013 due to politics of money. That was the only reason. They had sequestration budget cuts that were put out there as a doom scenario to convince the political parties to come together on a budget. They couldn't do it. And it was a 20% across the board budget cut, which included DOD. So many DOD R&D projects were canceled in 2013 because they couldn't agree on a budget. So the R&D projects were cut, and HAARP was one of them. We were under budget on time in one of their premier programs, but the politics of money got in the way. So the HAARP program and site then restarted after a full shutdown just 9 months later in 2014 with a lot of funding from DARPA, the Defense Advanced Research Project Agency. But it was taken down without power, totally cold, abandoned really for 9 months. But after 9 months, it came back up and ran beautifully. I couldn't believe it. And it's been in full operation ever since. The University of Alaska out of Fairbanks has the Geophysical Institute, who we were always partnered with academically, and they took over the HAARP program and all facility operations officially in 2015. So HAARP and its entire facility is run by the University of Alaska Fairbanks campus, which is 200 miles north of us. The HAARP program has remained in full operation with 3 to 5 research campaigns per year and more since the restart in 2014. And I am currently, Steve Floyd, that's me, I'm currently a part-time consultant and part-time chief engineer to the HAARP program. And sorry, all HAARP conspiracy theories out there are completely false and quite ridiculous. There's simply no conspiracies going on. There's nothing nefarious happening. Okay. The HAARP program was a joint program with the Air Force Research Lab, the Navy, the Office of Naval Research, and DARPA. And it's currently operated by the University of Alaska Fairbanks. And here we have radio science research in Alaska. And this is an early morning sunrise view looking over just a part of the 180 tower HF transmitting array at HAARP, our biggest instrument, but by no means the only instrument at the site. The site is a 5,500 acre site with capability from DC to light. Okay, so why is HAARP important? Well, HAARP is important because it's the USA's only state-of-the-art radio science research facility with premier technical capabilities from extremely low frequency, ELF, through microwave frequencies, including radar and optical light experimentation. So we have transmitters, receivers, diagnostic instruments, radars, really covering the span of DC to light. It's an enormously capable and state-of-the-art site. And it is the premier and only premier radio science facility for the United States. It has a unique high-power HF transmitting system that we call the IRI, Ionospheric Research Instrument, which is capable of temporary ionosphere modification and study for radio science research. We have comprehensive diagnostic instrumentation on site. Much of it runs 24 hours a day, 7 days a week, collecting long-term observational data. But that includes instruments such as a magnetometer, rheometers, radar imaging devices, receivers, ionospheric sounders that run all the time, satellite receivers, general purpose receiving systems, arbitrary waveform generation, reception for digital modes, etc. So we have just an enormous capability over the entire electromagnetic and visible light spectrum. We have receiving diagnostic instruments that typically run 24/7, 365 days a year. Receivers here, collecting valuable long-term observations of the electromagnetic spectrum, very useful. The facility, the HAARP facility, is located in a region up in Alaska where the auroral oval and mid-latitude ionosphere are within view. It's an optimum location for most radio experimentation involving the ionosphere. This is why the site was built in Alaska. There's a concentrated ring, like a donut with a hollow hole, that sits about the North and the South Pole. And this concentrated ring is a concentrated ring of ionosphere called the auroral oval. Much of the visible aurora light is a byproduct of this auroral oval and energy from the sun, exciting molecules of oxygen and nitrogen gas. So we're at a latitude in Alaska where we can point our instruments with directional antenna patterns into the auroral oval, experiment with that concentrated ring. And then when the oval moves farther north and goes out of our view, we can get mid-latitude ionosphere. It's just perfect. And so the remote location in Alaska provides a wealth of research opportunities with low man-made noise, as you would expect, and very low probability of causing HF radio interference to any service because we're in VIS. We're beaming mostly vertical, and then almost that energy comes right back down into the state. So we don't bother too many people. Okay, quick. I'm not going to go through this entire slide, but just a quick look at the history of the HAARP facility on a timeline basis. In 1990, starting at the left, the site was authorized for design and construction by the U.S. Congress. In 1993, construction began. In 1994, the initial 18 towers and 18 transmitters were built under contract by 94. And by 1995, HAARP attempted its first transmissions. Well, things didn't go very well. And as I joined the team in this time period, it quickly became obvious that subcontracting out this work was never going to work. Subcontractors have a statement of work. They want to get it done, get the profit, get out. And we needed innovation on top of innovation on top of innovation. And we needed a dedicated design team that was nimble and innovative, that could respond quickly and solve problems. And we were going to have to do that in-house. So we hired up a staff and took everything back from the contractors who crashed and burned spectacularly and couldn't make anything work. And we took everything in-house, took it all on ourselves, and selectively subcontracted manufacturing, and that saved the project. In 1999, we had added at that point 30 additional transmitters to the original 18. At 48 transmitters, about 60 megawatts ERP, lots of good science going on. The site was running beautifully after a massive amount of redesign and some rebuilding. And then in 2003 to 2007, we went into our final expansion, which was from 48 towers, 48 20 kilowatt transmitters, to 180 towers and 180 transmitters, to the full 42-acre phased array size, and achieving our 5 gigawatt ERP. And so we successfully completed that on time and under budget in 2007. In 2013, of course, we had that brief and painful and highly inefficient shutdown due to the sequestration budget cuts, politics of money. In 2015, UAF out of Fairbanks, the university, took over the site, all operations in 2015 and 2017, first active major experiments under the university's management. And in 2021, on the right side here, we got a major grant from the National Science Foundation to create what's called SAGO, the Sub-Auroral Geophysical Observatory, and HAARP is a key component of that work. And in 2022, they reestablished open houses. So that's the basic timeline. Now let's go north to Alaska, shall we? Alaska is a beautiful state. Strangely, I was born there as a child of an Air Force officer, but we moved away when I was 4, so it was great to get back such later in life. So the HAARP site is located up in Alaska, as I mentioned, because of the fact that it is a $300 million facility. We wanted that on U.S. territory, but primarily it's the northernmost state that gives us that look into the auroral oval, concentrated ring of ionosphere that causes the polar flutter that we hear so often. And the aurora borealis is sighted along the oval. We can power beam into that, do great science, groundbreaking shortwave and HF radio science. But when it goes too far north, we can also get mid-latitude ionosphere and do groundbreaking research there. Now so we're located here in Alaska, just northeast, about 200 miles east-northeast of the Anchorage area, and just outside the town of Glen Allen, in the little town of Gakona. So notice that we're about 200 miles south of Fairbanks. And if you go down to the coast, we're about 150 miles north of Valdez, Alaska. So we're in the southeast quadrant of Alaska here. This site was not chosen by accident. Back in the Cold War, they were building HF over the horizon backscatter radars. And the US was deploying a large system called the FPS 118. They had built a 3-sector site in Maine, and they had built a 3-sector site in Northern California, Southern Oregon. And this was to be the northern sector site looking north over the pole, a 2-sector site looking for launches of intercontinental ballistic missiles and aircraft in the Cold War days coming over the pole. So this site for HAARP was going to be the transmitter site for the ANFPS 118 radar. The receiver site was about 50 miles to the east near Tok, Alaska, near the Canadian border. They only got the all-important environmental impact statement done, and they were starting to build a power plant building. No RF was at the site when the Cold War came to an end, and HAARP was able to modify the environmental impact statement and move right into the transmitter site, and that worked out just fine. One of the challenges here is permafrost. We're in a permafrost area. We're so far from the coast, meaning that the only stable soil is frozen earth down to about 100 feet deep. And so in order to anchor buildings and towers into stable ground, we have to build in a permafrost environment. It has significant impacts on construction methods, timing, and costs. And we use devices called thermosiphons to anchor into the permafrost crust for towers and foundations for buildings. We'll talk about that, but that's a big challenge, which has been met. And this location provides that wide variety of ionosphere and space conditions that open up a wealth of research opportunities. The picture on the right here, that's an actual photograph over the HAARP site. You can see the just incredible aurora borealis painting out that auroral oval right over top of the HAARP site. That was a very common scene in the winter when it's dark. Okay, this is a view of the HAARP site in summer 2003. The river you see on the left is the Copper River. It is known for the famous Copper River red salmon, which we were able to catch and eat quite often. You see our operations center building, which says power plant, operations center, electronic labs, offices, and a kitchen. No bunks. We stayed on the local economy. About a third of the mile up the road here, you see this is the 48 tower configuration, our mid-level build, other HF, that's a big TCI antenna. Other science pads on these roads here, aircraft alert radar we'll talk about, another big HF pad. We have diagnostic pads for satellite, radar, and ionospheric sounders, and so on. Now, if we go up to summer of 2007 to the as-built site now, you notice we've added a lot of things. We've got a new science pad coming off the main operations center building. That's a big UHF incoherent scatter radar to actually three-dimensional image the plasma of the ionosphere, so we can see what the ionosphere is doing in real time, and that's very interesting. Notice how the HAARP array has expanded greatly here. We've now moved to 180 towers in a 12 row by 15 column array with 30 transmitter shelter buildings. We'll talk a lot about that. So that's at its final size. And that's a 42-acre gravel pad you're seeing there. We're up so high. And then the science pads grew too that you can't see. Okay, so HAARP, it's a research and development site. It's an RF sandbox is what we like to call it. It's a radio science research site that is used for fundamental research into radio science with some, but not total, emphasis on the ionosphere and HF radio. But we also do a lot of satellite and deep space research work as well with the great capabilities that we have. So the sort of the mission statement of HAARP with its major instruments is using the ionosphere as a nonlinear active medium, the HF transmitter can generate secondary radiation sources at ULF, ELF, VLF, visible, and infrared frequencies. So what does that mean? Well, one of the fundamental experiments that HAARP runs is if I wanted to build a transmitter at an RF frequency of 100 hertz, there's a problem. The wavelength, it's too big. And to build an efficient transmitting antenna with low loss that can handle power and give you a useful radiation pattern, the wavelength is just too big. You just can't build it. It'd be many hundreds of miles long, and you couldn't get it high up enough off the ground. So there's a technique where you can take high power HF radio and you can put a modulation in, and a simple example would be a 100 hertz square wave. So AM square wave, 100 hertz. So my 5 gigawatt ERP is going up and down at 100 hertz. And I might be transmitting at 6.4 megahertz or somewhere thereabouts. So that amplitude variation stimulates the free electrons in the Earth's ionosphere at our modulation rate, and it radiates RF, useful coherent RF, at our modulation rate out of the ionosphere. It's only, probably a handful of watts, but it's enough RF to receive and to use for many different applications. And we can also chirp in this example from less than 1 hertz RF, all the way up to 30 kilohertz and get RF back immediately during any sweep rate. So it's HAARP is just masterful at generating low frequency RF using high power HF. And we generate that RF at our modulation rate. And many complex waveforms and patterns are used to get the efficiency up, but that's the takeaway. You can build lossy receiving antennas out of ferrite rods and loop sticks, like a loop stick, and coils of wire, and you can have a negative 20 dB gain receiver antenna that's very useful and works fine. But at negative 20 dB gain, it would be a dummy load for transmit and would just burn up with that much loss. So we can't do that for transmit. Okay, HAARP can also produce radio wave propagation effects on demand and create new signal paths spanning the HF, VHF, UHF, L-band, and microwave frequency ranges. So HAARP really has very vast capability here. We can do things ULF, ELF, VLF on the left, things like submarine communications, underground radars, techniques that we've demonstrated many times, radiation belt interactions. We're transmitting in the big HF array in 2.6 to 10 megahertz. Then, of course, we have the HF, VHF, UHF. We can change propagation. We can work with radar and digital communications modes. And then we can also do a lot of optics work. We have optics transmitters and receivers as well. So we really have, we're an emergency high power radio technology for the next generation DoD system spanning 15 orders of magnitude of the electromagnetic spectrum, DC to light. It's more than just the HF transmitter. Okay, HAARP is not the only site that does this high power HF, stimulate the ionosphere and experiment with it. It doesn't hurt anything. It doesn't bother anything. It doesn't damage anything. And it doesn't have any effect on the weather or anything like that. But it's just enough RF to get a cause and effect study research going with the ionosphere. We're no longer having to passively observe it all the time. So HAARP, this is an interesting graph I wanted to share with you. The vertical axis is effective radiated power. And here we're in dB above a watt, dBW, not dB above a milliwatt, dBm that we're used to. This is dB above 1 watt. And that's the vertical axis. And then on the horizontal axis is HF frequency transmit capability. So effective radiated power versus transmit frequency capability. Not to say we transmit in all these places. The final HAARP build out in 2007 is the blue line here. The ERP goes up as the frequency goes higher because of the fixed aperture of the array, more aperture, shorter wavelength at the higher frequencies, you simply get more gain. So HAARP has the widest frequency capability and the highest power of other similar systems in the world. There's a similar system that's not nearly as advanced as HAARP is or as big, and that's in Europe, in Norway, Tromsø, Norway, called ISCAT, E-I-S-C-A-T. ISCAT has the operational capability in the orange lines here, less ERP, less frequency range, but they do ionospheric modification and study research as well. Strangely, they don't like to accept DoD contract money in Europe. I don't know why, but HAARP, certainly will accept that. Then I said Sura, Ukraine, but that's actually Sura in Russia. It's not in Ukraine, it's actually in Russia. Need to fix the slide. But so the Russians have a site that has this much lower ERP versus frequency range to experiment with the ionosphere. Before we got into the recent conflict in Russia in the early 90s, US experimenters were going to Sura in Russia and operating experiments at that site. It's very crude, very, very crude, very limited in its capability, but it does generate useful ERP. And they have a small number of very high power HF transmitters feeding cage dipoles held up by telephone poles. And They have one feature, however, in their transmitters that we don't have, believe it or not. And what that one feature is that people kept reporting back to me, I've never been there myself, but people that have gone there and experimented, they keep raving about this feature they thought was useful. And I said, well, what is it? Maybe we could add it. And they said, well, the feature is whenever you open up the back of one of their large HF tube type transmitters to do maintenance, there's a very handy accessory inside the back of the Russian transmitters, and it's a bottle of vodka. And you can take a little swig, and apparently that helps. So that's a feature we have not added at HAARP, as you can imagine. But they are active in Russia. Now we have two green dots here, Arecibo, and I'm sorry, three green boxes here. Arecibo used to have an HF transmitting site located on a shoreline, not at the big dish. The big dish was a receiver at this time, and they had a transmitting site only off by the coast, but it kept catching fire in their transmission line and burning down. And then a storm, hurricane took it out in the early 2000s. So they lost that capability. The two red dots, there was a limited system run by UCLA up in near Fairbanks called High Pass. That's long gone now. And then the yellow line is the ERP capability at the 48 tower level that we achieved in 1997, 98. So HAARP is the most sophisticated, highest powered site. We do not transmit in the ham bands. It's all the software locks it out. Okay, let's drill down to the HAARP site and let's talk about the HF array that hams would be most interested in. So here's a cross section of a HAARP tower, and I'm going to work my way from the outside in to the transmitters. It's the best way to do it. A HAARP tower is approximately 85 feet tall. The tower is at ground. If we go to the very bottom, remember I commented we have to anchor into permafrost. That's the only stable soil we have. So what we have to do is wait till the winter time. And when everything, the top active layer of soil, about the top 5 to 8 feet, is not melted, it's frozen rock solid throughout 6 months of winter. When everything is frozen up solid, we position, locate where each tower is going to go, and then we drill a 30-foot deep hole, and we then implant in the hole a passive device called a thermosiphon. Now, this is a steel pipe. It's about, I don't know, 14 inches in diameter. And it's just a hollow special steel pipe with this arm and a radiator that comes off to the side. It's filled with 500 pounds per square inch of CO2, carbon dioxide. And what happens is in the summertime, it doesn't do anything. In the wintertime, however, when the outside air temperature gets below about 0 or minus 10 Fahrenheit, the CO2 under that pressure starts condensing to a liquid, and it drips down to the bottom of the pipe. And when it gets down into the permafrost layer, that's down to about maybe 80 to 100 feet. That's stable and always frozen. It's now about 29 degrees Fahrenheit plus, always in the ice. So it turns back to a gas. Well, what that does is that allows the heat to be sucked out of the ground and radiated out the arm, and it's all like a passive system here. And so during the winter time, we're sucking heat out of the ground, super freezing us into the permafrost crust giant ice ball, and the radiators radiate off the heat. Now in the summertime, it goes dormant, it goes inactive, doesn't do anything. The process just stops. So it gets through the summer, no problem. And then the next winter, it just starts automatically working again. The colder it gets outside, the more it sucks the heat out of the ground, super anchors us into that stable permafrost crust. It's pipeline technology taken to the next level. They had to use these for the Alaska pipeline in various places. Okay, 15 feet off the ground, we have a ground screen. It's an 18-inch square AlumaWeld wire screen that's suspended above the ground 15 feet up. That's grounded to the towers. The towers are at DC ground, and that's our reflecting ground plane, cars, people, buildings, for the transmitter shelter buildings, everything is underneath the ground screen. So we have a perfectly flat ground plane, extremely conductive, looks like a flat metal sheet at HF. So then as we move up the tower, we go up about 43 feet, and we have what are actually 3 wires in parallel for each side of the high band dipoles. This is sort of a cross-section view. So we actually have crossed dipoles to support circular polarization. So if this is a north-south cross-section, there'd be an east-west identical construction coming in and out of the monitor at us. So always remember, all of our dipoles, we have 2 crossed dipoles so we can support circular polarization. But this is a cross-section in only one of those 2 planes. So here's the high band, 3 wires shorted at the end, and this is our north-south dipole, and there's an antenna matching unit here in a round can, and that has the Balun function, impedance matching, and vacuum relays to where we can disconnect it when we go to the low band. Now, when the low band is active, the high band dipoles are floated with a static drain coil. They vanish. The low band is then switched in. That's a 3-dimensional cage, fat bow tie dipole for wide bandwidth. It has a boom at the top, you'll see, and then there's a 3-dimensional cage making a fat 3-dimensional bow tie for the dipole. And again, that's for the low band, which is 2.6 to 8.4 megahertz. The high band is 7 to 10 megahertz. So we switch to the low band. Of course, now we're trying to stay a quarter wave off the ground plane to get reinforcement of our energy up. So the high band is lower on the tower to stay a quarter wave on average off the ground screen for maximum radiation up. If we were a half wave, we'd have a null facing up, the opposite of what we want. But this is trying to stay a quarter wave off a ground plane to get reinforcement of the energy transmitting vertically up. So the high band, the elements are sized for the 7 to 10 megahertz, and roughly a quarter wave off the ground screen, 7 to 10. For the low band, 2.6 to 8.4 megahertz, and it's roughly a quarter wave off the ground screen for those lower frequencies, and there's a matching unit for each dipole with the same characteristics. They're all fixed tuned. Okay, so what does that look like in real? Well, here's a picture. Let's look at this tower on the lower right here. You see the white, whoops, went too far. We see the white base here. That's that thermopile, that hollow pipe, that thermosiphon that's been planted in the ground during the winter time. It's backfilled with some wet sand, and then it super freezes itself in over the winter. Here's that radiator arm, and there's 2 actually radiator fins, the little fins here. That's what radiates the heat out in the wintertime, and it does nothing in the summer. So there's our thermosiphon firmly anchoring us into the permafrost crust. Then you see the tower going up. It's a guide tower. You see guys from adjoining towers. Above the ground screen, the guys are Philly-strand, the non-conductive Kevlar-centered guy wire, if you will, which is transparent for RF. But below the ground screen, as you can see here, we transition into a steel guy wire to be bolted at the base of the tower. You see some RF distribution and fiber optics cables. You go up the tower, and you'll see the ground screen. You can sort of make out this ground screen here, the 18-inch square AlumaWeld ground screen. So it's aluminum on the outside, but steel core, all crimped. And that's our ground screen grounded to the tower. Then as we come up the tower, let's go over here to the left. We go up the tower. You can see 2 round, well, first there's small boxes. Those are high band, low band switch boxes. We're fed by 1 5/8 corrugated solid foam dielectric coax. Standard 1 5/8. This is made by RFS, but it's like Heliax coax, 1 5/8 solid foam, no pressurization. And so we have 2 runs coming in. One is east-west and one is north-south. We come up to the switch boxes. We can switch to either high band or low band. And then for the high band, we have 2 of those round cans. Those are the matching units, one for north-south dipole, one for east-west dipole. And then we have a little box over here that's called an even mode load we'll talk about. And then we go up to the low band. You can see the boom that's all insulated from the tower. There's a 3-dimensional cage that's hard to make out, but we have our cross dipoles for low band, much bigger, quarter wave off the ground screen. 2 low band matching units, same architecture, but a different design, obviously, for the different frequency range. And a larger reject load box here called our even mode load for low band, which we'll be talking about. In the background, these white trailer-like buildings are transmitter shelter buildings. They are not trailers. They're custom built with a single cooling blower, armor plating in the sides, a supply duct in the floor, a return duct in the ceiling, and 6 transmitters, 6 20-kilowatt transmitters in each building. They're only in this form factor just to get them on flatbeds. So they're very custom transmitter shelter buildings for this use. And again, this is just a part of the 42-acre phased array here. Okay, let's zoom in a little bit here and talk about a tower. So again, the tower is at ground, their guide. And you see the 2 switch boxes on the bottom here. One is our east-west switch box to switch between high band or low band. The other box is a north-south switch box to switch between the north-south high and low band. The antenna matching units, you see 2 for the high band here lower on the tower. They take coax 1 5/8 EIA flange in, 20 kilowatts, and out to the dipole. And then you see the low band matching units. These are fixed tuned. In other words, there's only vacuum relays inside to release or connect the dipoles. Beyond that, they're completely fixed tuned. There are no motors, there's no taps or anything to change, and they're pressurized once with dry air. So many of them are flat now, but that's okay. It just makes sure the O-ring seals are good. Now look at these square boxes here. There's 2 smaller square boxes for the high band matching units and 2 larger boxes for the low band. Well, we discovered we had a problem. The government only wanted 1 array built, 1 single array, but we had to break it up into a high band and a low band to get the pattern and the VSWR that we needed. So rather than having 2 separate arrays of 180 towers each, that was too expensive. So we had to stack them. And we could make the high band disappear by floating the half dipoles and let the low band be active. Or we can get the low band to disappear by disconnecting the half dipoles and connecting the high bands. And then the low band disappears because it's not resonant and it's just terminated with a drain choke when it's released from the matching unit. So we had to stack them. But this brought about a problem we didn't expect. In order to prevent unintended grating lobes in the high band radiation pattern, the towers had to come closer than we would like in low band, much closer than we would like. So we gave up some gain in the low band in order to make 1 array that could do the high and the low band to control cost. Well, and the artifact that we didn't expect and our models did not show was that when the low band dipoles are only 12 feet apart at the ends, dependent upon operating frequency and phase, we were getting a buildup of completely unexpected even mode RF power on the low band dipoles from neighboring transmitters. And this is a mutual coupling effect by proximity, and dependent upon frequency and phase, we would get hot spots in the array of this even mode power that's coupled onto antennas from neighbors only. It's a mutual coupling effect. Now I'm emphasize even mode because that means the voltage polarity in this mutual coupling case is plus plus on each side of the dipole or minus minus on either side. The same voltage polarity on both sides of the dipole. That energy cannot radiate. What can radiate is odd mode, which is positive on one side, negative on the other side of the dipole, or it flips, where you always have opposing voltage polarities on either side of the dipole. That's odd mode. We get that coupling as well, but we can deal with it and tune to it. But even mode power from mutual coupling cannot radiate, but it's got to find a return. So it was returning at these hotspots through ground currents and causing voltage maximas and current maximas that were burning up our first iteration of antenna matching units. So we had to control this even mode power, and we did it through reject loads. We built a 4-port hybrid coax transformer, no ferrite in the system at all. None, because we can't let ferrites saturate potentially and cause harmonic content. Not allowed. So no ferrites allowed. Everything had to be ferrite free. So we built a 4-port hybrid transformer using some tape wound Teflon special coax from Times Wire inside. They gave us a turns ratio for impedance management, gave us the Ballon function, and also gave us the even mode power reject port to waste off that even mode mutual coupled power that we have to control because of the close proximity of the dipoles in the array when it's there. If the even mode power is not there, the loads do nothing. We still see the odd mode coupled power as a change in SWR from the neighbors being on. But anyway, so that was a big breakthrough, and we met that challenge, and that is a design that's now taken on life in other worlds. But anyway, so we have 2 sets of cross dipoles, the low band 2.6 to 8.4. That's the big booms and a 3-dimensional wire cage at the top. And you can switch to high band 7 to 10, unique fat bow tie geometry. Everything is welded and designed to survive 100-mile-per-hour winds over 55 mile per hour with a 1/2-inch radial ice. Okay, what does this matching unit look like? Well, this was completely designed in our Washington, D.C. office, prototyped and tested up to 40 kilowatts into different loads. And it's a very innovative and unique design here. Again, everything's fixed tune. What you're seeing here is the can pulled off of this is a low band matching unit. So the O-ring seals, you can see one at the bottom. It's completely moisture sealed, but we took the can off. And at the top, you see our 4-port hybrid transformer wound on air. This is just a G10 fiberglass supports in the middle. And then we have the coax. This fin thing at the top, that's just to radiate some heat off because that was a high current joint there. But this is our 4-port hybrid transformer. The RF comes in on the bottom right here. You can see that there's hidden a vacuum variable fixed cap. We have some silver plated coils. You can see one of the vacuum relays here, that white square, and a spark gap and so on. And that even mode reject port is coming out, is coming out this tap right in the center, this rod that comes down and goes down to a 7/16 DIN. That's our even mode reject port. It's a 50 ohm output port to a 50 ohm convection cooled load. And if there's even mode power there at any level, it just goes out that port. If there's no even mode mutual coupled power, then it doesn't do anything. A revolutionary design. The insertion loss at worst case VSWR, which is almost infinity on the balanced output, the insertion loss of this entire matching unit is 0.2 dB, worst case. Worst load impedance, 0.2 dB. That's extremely low and no ferrite. Okay, let's talk about the transmitters. Each shelter building hosts 6 transmitters. Everything is operated over the internet, or I should say over a local area network, and the site itself can be operated remotely over secure internet. So everything is network controlled. This was revolutionary in 1993 when we started designing this. And it's now, old hat, but all the transmitters are operated over a local area network with beautiful GUI software. So here's a look at a transmitter building. You walk in, you see 3 transmitters on the right, 3 transmitters on the left. Each one of these transmitters is 20 kilowatts and can cover 2.6 to 10 megahertz continuous tuning. Now, I can guarantee you we do not transmit in the ham bands. It's locked out in software, and if anybody did, they would lose their job immediately. That was absolutely never allowed. So we've never transmitted in the ham bands. We do have a ham station, KL7ERP, with a Yaesu radio that we run at the site, but through a OCF dipole, but not the big transmitters. Each transmitter has dual independent outputs. So there's actually a 10 kilowatt output on each side of a single HAARP transmitter. So they're 20 kilowatts, but the left side of the transmitter is an independently tuned east-west output, always to the east-west dipole on the tower that's married to that transmitter. And then the right side 10 kilowatt independently tuned amplifier is for the north-south dipole on that tower. And we can control phase to set up our polarization as to how we want to use those orthogonal dipoles. So each transmitter is actually 2 independently tuned 10 kilowatt amplifiers. So there are 4 IMAC 4CX 10000D tubes per transmitter. That's right, 4 IMAC 4CX 10000D power grid tubes per transmitter. Now, why 4? Well, one 10 kilowatt side, independently tuned for east-west dipoles, is running 2 4CX 10000Ds, grounded grid, cathode driven in a push-pull pair. That gives us many advantages. But then again, on the right side of the transmitter, we've got our north-south amplifier, and it's got the same thing. 2 4CX 10000Ds, grounded grid, cathode driven, push-pull pair. And so that's a total of 4 active tubes per transmitter. The drivers on each side are solid state broadband up to 1 kilowatt, nominally 500 watts drive to the final. And then driver before that is 30 watts, nominally driving at around 10 or 15. So 4 tubes times 180 transmitters, that's 720 IMAC 10000Ds that are active in sockets at the HAARP site. And it's 100% IMAC site. And the tube life is very long. We do get failures, which I'll talk about later, but not very often. And we can get those tubes rebuilt at IMAC with no problem. So we also have an automatic antenna tuner built into each transmitter, each 10 kilowatt output that can handle a VSWR conjugately matched 5:1. We can do graceful degradation well above 5:1 to infinity. Now, each transmitter has a bandwidth of 200 kilohertz. 200 kilohertz, that's huge. That's bigger than some ham bands. But we had, this is our actual operating bandwidth that could support a waveform. Could be 200 kilohertz wide if we wanted. And then as we go up to 10 megahertz, our operating bandwidth is 500 kilohertz. So if you think about an AM broadcast transmitter, an international broadcast transmitter, it's going to have about 20 kilohertz of bandwidth. 10 kilohertz on the lower sideband, 10 kilohertz max on the upper sideband, that's 20 kilohertz. Well, we have a useful bandwidth of 200 kilohertz and it goes up to 500. We don't use that much bandwidth, but we have it available, and it really reduces the effect of that mutual coupling problem in the array to have such large bandwidth. Look at the harmonic and spurious in band. Our harmonic and spurious minus 80, just like a broadcast transmitter, but out of band down to a minus 120 dB, that's incredibly clean, and minus 150 dB down from 88 to 200 megahertz, where the wildlife tracking and broadcast folks live for this rural part of Alaska. And the modes of operation, these are effectively arbitrary waveform generators. We can do continuous wave, CW, we can do full carrier, we can do AM, we can do FM, we can do phase mod, we can do pulse mod with user selected rise and fall times. And we can do them all simultaneously if that's what the experimenter wants. Enormous capability here and precision capability. And we have 6 transmitters mounted in a shelter building. As you see when you walk in, there's a rack on the left. That's all of our networking and phase control. 3 transmitters left, 3 transmitters right. There's a door open in the back to let some light in. There's a common cooling source plenum in the floor. Back in the left corner is a single 3-phase motor with one of the largest squirrel cage blowers you'll ever see. It sucks in outside air, charges the floor plenum, shoots air up through all the transmitters through holes in the floor. The heated air, after passing over the solid state and then tubes, comes out into a ceiling plenum with these black exhaust hoses. And then that air is mixed with outside cold air if necessary to supply a plus 50 Fahrenheit inlet air temp. If it's in the summertime, we can't cool the air, so we just blast it all outside. And here's a look at the transmitter shelter building in the lower left, armor plating in the sides, good R value. And you can see the 1 5/8 coaxes coming out the side to the associated towers. One key point here is there is 1 transmitter permanently connected to its tower, and we have 3 towers mounted on one side of the shelter building and 3 towers on the other side. So the transmission lines fan right out and go right up their towers. And then the next set of 6 towers has a shelter building in the middle of those 6 towers. So all the transmission lines feeding all the antennas are built to an electrical length, so it's a constant and we can ignore it. So we only have to control the phase at the output of the transmitter. Everything else is a constant. Okay, this is what the operations center looks like. This is up in Alaska where they run the site. We have beautiful graphical user interface software to run all the transmitters with, which I'll show you examples of. The main site operator sits in the middle here. There's a big 4 display thing up at the top for everybody to see the whole array and status and so on. And then to the right, we have power plant control. We have off-air spectrum analyzers, other test equipment, camera to look at the generators in the generation bay. Over the left, we have environmental control and aircraft alert radar. The chief scientist would be sitting to the left here behind the operator, and then we have other major scientific rooms. But this is the main control center. We can use and often do run the site remotely over the internet with our chief operator who sits in Oakton, Virginia, operating it now through secure internet, oftentimes, but not always. And technicians just sit at the site, monitor things, and can run out and make adjustments. But our preferred method is to operate from Alaska so we can respond more quickly and more innovatively during experimental campaigns. Okay, how do we keep track of 180 transmitters? And each transmitter is a dual transmitter. So I really have 360 independently tuned 10 kilowatt amplifiers. How in the world do you keep track of this many transmitters in a global view? Well, we innovated like crazy on the GUI remote control software. And I grabbed this shot early on. It's very rare that we would have a transmitter off the air, but we have 3 that are off air in this early shot. And these 3 boxes that are white with the capital A, that means antenna band open, meaning all the vacuum relays on all the antenna matching units are open. So we cannot get RF shoved back into this off transmitter from its neighbors that are antennas or space close. So that means that it's obviously off and the antennas are disconnected. So, so that's what those 3 A's are. But what you're seeing here is 180 transmitters. And how is it 180? Well, it's, let's see, 1, 2, 3. Yeah, so it's 15 vertical columns and 12 horizontal rows. And up, if we go to the top left here, we see A. So this is shelter building A, and we call it shelter building A1. And you would walk into the building, that white trailer on the right side here, and the first 3 transmitters would be on the left as they are here, or the first 3 transmitters on the right here. And each transmitter is given a row column nameplate or license plate number that we refer to them to. So this transmitter up in the left corner in shelter A1, it's 0101. That means it's column 1, row 1. The next transmitter is 0201, column 2, row 1. We go drop down from him, we're still column 2, but now we're row 2. So that's transmitter 0202. So you see how the transmitters have a name, and it's their row column intersection numbers, how we know all the transmitters. So if I come all the way over here to the top right, that transmitter in shelter echo or E1 with the 6 transmitters, that top transmitter is transmitter 1501 or column 15, row 1. So this is geometrically correct. If you're a bird over the array and you're looking down, the shelter buildings are geometrically correct. A1 through A6 on the left side and B1 through B6 and so on. The transmitters are geometrically correct, and it maps to antennas that are positioned in the same way. So if we look back at one transmitter in the top left corner, the green is the forward power. It's 10 dB per box. So up and down is north-south, left and right is east-west. So green says what our forward power is, and the blue is the reflected power overlaid on top of forward power. So up and down is north-south, left and right is east-west. So you can see in this transmitter 0101, we have 1 box of green and 3 boxes of blue. That doesn't look very good, but it's not bad because this is 10 dB a box. So full all up to the top is 10 kilowatts, and 10 dB down is my reflected power. Well, that's a 2-to-1 SWR. Now the east-west is a little bit higher. It's a little worse than 2-to-1, but you can sort of see how we took the reflected power graphs that are kind of orthogonal graphs and made them form a box. And then we did the same thing with the forward power graphs, made them form a box. And so you can sort of see now that everybody that's active is at full forward power, and you can see the reflected power characteristic. And notice the reflected power is better in the center of the array. It's generally lower in blue, in the amount of blue. And so that tells us that it's doing exactly what we expected. We designed the matching units to accommodate, it's one design, so it accommodates the situation in the middle of the array. And you can see RF is on and everything else. Now I can click on any one of these boxes in reality and bring up a control panel for that transmitter and work with it. And again, the 3 with the A's in it are offline, very rare. Okay, now we have another innovative capability here that's never been done before. And again, this is where amateur radio comes in. You know, as hams, we're always thinking about how can I make this better? How can I innovate? What could I do that would be cool? And so that's what I did, because I had to innovate like mad to get this site built and have it built and be so reliable. And so one of the innovations we came up with was we meter just about everything we can in the transmitter. Every transmitter we meter, of course, output power, reflected power, driver reflected. We measure temperature, airflow, grid voltage, grid current, screen voltage. I mean, you name it. 480 3-phase is the prime input power. 480 volts AC 3-phase is the prime input power to each transmitter. And about 62 amps per phase would be a normal power consumption with a full power carrier of 20 kilowatts out of a single transmitter. But we monitor current and voltage on it. We monitor everything. So what we do is we can assign a color temperature graph to anything we meter and show it for all transmitters. So what you're seeing here is PA1, that's an east-west output. And over to the right is PA2, that's our north-south output. So here is 180 PA1s in the geometrically correct position, like you're a bird looking down. And here's 180 PA2s, north-south RF amplifier output powers, what we're metering here on the right. And then we have the corresponding reflected powers for the master output. So this is PA1 reflected powers. Notice it's a cool color temperature, much lower. You can see the scale on the right here. And so what we're seeing, and for PA1, top left corner again, 0101, transmit power 10.0 kilowatts, great. But I come over here to the top left corner of the reflected power, and there's 0101, and it says 2.7. Oops, I got 2.7 kilowatts of reflected power for his 10 kilowatts up here. So that's a little high, and you can see the warmer blue there, that's a higher value. Now I got a real problem that I need to go work on down here in the lower center. PA2, north-south. I'm down here at transmitter 0112. And so north-south, 0112. And forward power, 10.3 kilowatts. Reflected power down here, oh, that's green. That's much higher in value. 4.6 kilowatts reflected power down here. So I said, okay, I need to go fix that tower. That's an outlier. So we applied this color temperature diagnostic to all readings that we get from the transmitter to find outliers. And then we can then go and work on those transmitters to get them back in line to optimal performance. And that reduces failure rates and increases reliability. And it just works great. In the forward power area here, you can see some boxes that are orange. They're a little bit less than 10 kilowatts. For example, here is transmitter where my pointer is 1506, and he's only at 9.4 kilowatts forward power. So we know we need to go look at him because he's low and he's not making his program power. So this is a very, very powerful color temperature diagnostic technique that's unique to HAARP. But the innovation doesn't stop here. So the other thing, I mean, we innovated thousands of things that are just off the charts, and to get this site built, just unbelievable innovation. But here, what we did was we said, okay, we need to know what our antenna radiation pattern looks like. Remember, we have a phased array here, a 12 by 15, 180 tower phased array. We can form a pattern by adjusting the phase of all the transmitters that we have absolute control of, with phase lock loops wrapped around each transmitter, all done digitally over a local area network. So we can program the output phase of every transmitter. So not only does that allow us to point the beam in different directions, but it allows us to make the beam fat or narrow or like a pancake, or we can make it different shapes, and we can point the beam in different directions, all by adjusting phase, and phase only, no motors. So we said, okay, we have a neck model and it's really good, and we know what the phases need to be for different patterns and gains, but how do we know that it's really doing what we told it to? So we had an innovation. This was not even in the spec, but we had an innovation, and we said, all right, we're going to add this capability, and we're going to take RF current samples off of each dipole, bring them down 3/8-inch heliax lines, do an A to D, bring it over the LAN, apply it to a NEC 4 model of the array, and we'll display the calculated pattern from the programmed phase and see if it aligns. And it does. And we flew test patterns with an aircraft up at 10,000 feet. The government did. And here's an example of a real-time radiation pattern with side lobes and its pointing angle. And here we're at 3.4 megahertz, all the different angles. The gain is 22.658 dB, and the effective radiated power is 6.378 megawatts. But what if we're doing split frequency operation? We can do split frequencies. We can transmit any random number of transmitters at frequency 1 with whatever modulation you want, and we can have the rest of the transmitters on frequency 2 doing something completely different. And the experimenters love this. And so here our antenna pattern measurement software shows us this, where here the largest ERP is the red. So that would be 6.8 megahertz, 4.702 megawatts. There's the gain and the pointing angles, all measured and then played into our model to give us this display. And then the lower green one is 4.5 megahertz, pointing angles, and a lower gain. So what an incredible tool to see your radiation pattern in 3 dimensions instantly with high accuracy that was proven by far field measurements. Okay, let's talk about the power plant. We have to generate our own power. We get 3-phase power from Valdez. It's only about 600 kilowatts, can't take pulsing. So we run our offices off the outside power and occasionally individual transmitter maintenance. To run all the transmitters, we have to turn on our own power plant. We have 5, that's right, 5 massive turbocharged locomotive diesel engines. They're EMD, 20-cylinder diesel locomotive engines bay off our ops center building, all compressed air start, auto sync. Each generator good for 3 megawatts. We need 4 of the 5 operating to run the entire transmit array. So that's about 12 megawatts of power to run the whole transmit array. The 5th generator is a spare. So you can see the total specs here, 5 EMD diesels. If I have all 180 transmitters with a full power carrier, 100% duty cycle, properly tuned, I'm going to pull about just over 9 megawatts from the power plant. And because our transmitters are only 42% efficient, no broadcaster would ever accept that. But we're all about spectral purity, so it's a linear amplifier system. But we would consume 500 gallons of diesel fuel per hour running a carrier at proper tuning, 500 gallons per hour, unless we have some sort of a duty cycle to slow the power consumption. But we have our own power plant, and it is this clean. It's beautiful. Okay, one of the problems we had with HAARP was, how do we guarantee 100% that we're not going to be a hazard to airplanes in flight? Well, you can't guarantee anything 100%. So the FAA said, well, what are we going to do here? Even if you did not interfere with a plane and the pilot claimed you put his flight at risk, you could still be shut down. So we said, okay, so let's figure something out here. So this is something that I came up with. This is called our Aircraft Alert Radar System. There is no hazard to flight that is known. There is no hazard to people or planes or navigational aids or communications that has been proven to be known. But we have to eliminate the possibility 100%. So what we decided to do was to stop transmitting automatically if any aircraft from 500 feet to 55,000 feet comes within 5 miles of the site. The software keys up, stop transmitting. And if we lose the track, we'll wait till it coasts out 5 miles and then it'll allow us to come back on. Or if we can track it, we'll wait till they get 5 miles away and then we come back on. So this is a political solution to a problem that doesn't exist, but nobody can blame us for anything this way. So here's the aircraft alert radar, all operated over the local area network. The first disc on this aluminum tower that you see, that's a TCAS, a collision avoidance system interrogator for standard transponders. We have a high power aircraft TCAS mounted on this plane. Gives us hemispherical coverage to track all active transponders on all planes with transponders to standard mode S, and gives us a beautiful radar track using our software. So we're tracking transponder pings, excellent accuracy for range, altitude that it's reporting to us, and azimuth angle DF'd. Then we have on a 30-foot Roan 55 tower here, we have a 60 kilowatt S-band maritime radar with the antenna pointed up to get maximum coverage in the vertical plane. And that is also tracking planes that don't have transponders. And we can see planes easily out to 50 miles and up to 55,000 feet and get excellent tracks. We also use ADS-B, the new GPS-based beacon, automatic dependent surveillance broadcast. We have ADS-B receivers. So we have 3 methods of tracking planes, and we automatically shut down if a plane gets within 5 miles of the site. It works perfectly. The FAA was mightily amazed at this innovation. Okay, I'm going to quickly go through the installation of the transmitters and wrap this up. So the HAARP transmitters were designed in our office in Washington, D.C. The contractor, Continental Electronics, failed massively on their first go, and they overran the contract massively. So we took the design in-house. We only kept the cabinet, the high voltage power supplies, and the tube deck and the tuning coils. We rebuilt the entire transmitter, redesigned the whole thing. Low-level RF, redesigned. Software, completely redone. Digital I/O, completely redone. Networking, completely redone. Everything completely redone except for cabinet, power supply, and tube deck. And so we then modified the 18 transmitters. We had one in Herndon, Virginia, in a test bed. We then went back to Continental, paid them to contract manufacture the transmitters for us, and they said it was one of the best transmitters they ultimately ever ended up building. These are our maintenance techs installing a transmitter in a HAARP shelter building. We installed all of the transmitters ourselves. So that's 3 of our staff rolling a transmitter in. Here's a HAARP transmitter in a shelter building. We first mount the power transformer. That's 480, 3-phase in, various high voltages out for the tube final. You can see the transmitter getting ready to be pushed back against the wall. There's inlet air from that floor plenum at the bottom. And the adjoining transmitter without the back covers on, you can see a tuning coil. That's a stepper motor driven tuning coil with shorting bars diagonal. That's spring copper coils against a silver plated brass rod. It's a very precision. That's the output L component of our antenna tuner for a 10 kilowatt final. And you can see the RF outputs up here, 1 5/8 CIA flanges, 1 for the antenna, 1 for a test dummy load. Okay, here's a side view of a HAARP transmitter. To the right, you see that coil we were just looking at for the output antenna tuner, stepper motor driven, high precision. You see a vacuum capacitor in the bottom center. That's for the output reversible L tuner. Then you see the 2 tubes, the air stacks, and then you see the plate tuning coil. It's a link coupled plate tuning coil and plate tuning capacitors, all stepper motor tuned and controlled with high precision. So here we are actually installing HAARP transmitters at the site. The transmitter shelter buildings were delivered empty, and we then installed all equipment ourselves. We brought the transmitters in, did a QA, and then we pushed them against the wall and bolted them to the floor. Here's with this HAARP transmitter on the left, the left side is the 10 kilowatt east-west amplifier. The other side, the right side, is a 10 kilowatt north-south Remember, it's married to one tower permanently with fixed delay coaxes, so they all disappear as far as the array is concerned. So in the center, we have breakers and meters, and at the bottom, we have high voltage power supply. The lack of the front panel is because we talk to the transmitter over the network. I would come into a shelter building, open the door of this rack, plug into a switch, open up my laptop. I'd log into the transmitter by its row column designator, 0101, for example. I could log in and do everything on my laptop. So here we're pushing another transmitter into place. Here I am doing some fine tuning and adjustments on the transmitters after they've been installed. Another incredible innovation here. I was able to come up with a technique where I could take a network analyzer and I could sweep an entire 10 kilowatt amplifier for gain, bandwidth, flatness of gain over bandwidth, and other aspects of the transmitter performance that I must have. And I could adjust stepper motor static offsets in the transmitter to tweak the tuning every 500 kilohertz. And I would tune it for a perfect swept response of gain, output power, and shape, and phase response, phase linearity on the network analyzer by using stepper motor offsets every 500 kilohertz, and then save it as a CAL file. And then we would do a spline fit interpolation between these points for frequencies that fall in the middle. We did the same thing for power output. We had precision calibrated coaxial dynamics power meters into dummy loads, and we did a precision power cal using the same method every 500 kilohertz to very precision watt meters, save those cal files, and again, spline fit interpolation. Bottom line is that these transmitters are calibrated like pieces of Agilent, HP, Keysight, Rohde and Schwartz test equipment. These are test equipment competitive capable transmitters in terms of the precision of the calibration. The scientists want this and demanded it, and we did it. You can see 3 transmitters behind me with the tube decks open as we're commissioning these transmitters. Okay, here's what a HAARP transmitter shelter building looks like. These documents on the front are QA sheets that are removed, but these are still hanging there, QA inspection and test sheets. The transmitters really are this clean. Every single building is this clean. 3 transmitters on the right, 3 on the left, that control rack, the blower in the back left to charge a floor plenum. That's our source air plenum for air cooling the transmitters, the black hoses above for the exhaust air into a return plenum in the ceiling. We mix that return hot air with incoming cold air from the outside to get a 50-degree constant inlet air temp. And in the summertime, we just throw all the heat outside and just take what we can get from the outside. And it's a very efficient, very rugged, very excellent setup in the transmitter shelter buildings here. And it can all be operated remotely over the internet, or over the local area network. Nobody needs to go out there unless you just want to go out and look or attempt to fix things. It's all operated 100% over a LAN. Here's an aerial view of the HAARP site. Again, we have capability DC to light, but we're focusing on this 42-acre HF transmitting array, creating that up to 5 gigawatt ERP for ionospheric modification and study. You see the 30 shelter buildings symmetrically through. So we have constant delay transmission lines from each transmitter to their respective tower. You can see the operations center building on the left. The power bay with those big generators is the low bay on the right, very well sound insulated. You see many other towers. This is our ionospheric sounder in the bottom center. This is our satellite pad here, incoherent scatter radar back here. The mountain you see in the back is Mount Sanford. It is not the big Denali. That's way too far away. This is in the Wrangell St. Elias National Park. It's Mount Sanford. It's about 26,000 feet high at the top, and it's snow-capped all the time. Beautiful, about 28 miles away. Okay, here's a view of the HAARP site. I was driving in one morning, and they had this nice frost over all the Philly Strand guys over the ground screen. You can see with this box shape here and all the other guys and everything, and the dipoles, the fat bow ties. And it's really busy looking, but there's quite an order to it. Okay, let's talk about the Auroral Oval briefly here. Remember, the HAARP site is in Alaska because we want a power beam into this concentrated ring of ionosphere called the Auroral Oval. It's created by the solar wind hitting the Earth's atmosphere and the Earth's magnetic field. causes this auroral oval to get concentrated into a ring, not a spot. And there's a complementary ring at the South Pole that tracks what the North Pole ring is doing. So there are satellites in orbit that give us mapping data that's relatively fresh of what the auroral oval looks like. It has about a jillion amps of current flowing in it in the ionosphere, and it's enormous interest for radio science study. And HAARP can do that. And when it goes too far north, then we get the mid-latitude ionosphere. Okay, here's a picture of that aurora borealis that's manifested along the auroral oval. This is an optics trailer at HAARP. And this is a dark night. And here you can see this beautiful green with some red mixed in aurora borealis. That is energy that's flowing from the sun down into that concentrated ring of auroral oval. And that concentrated energy is causing the molecules of gas to give off light, causing an aurora, painting out the auroral oval for us. Okay, let's talk about a couple of experiments here, then we'll wrap it up. So HAARP is a general purpose research site that's just filling up the physics journals of radio science like crazy. Some of that information does find it into the ham world. We are partnered with Ham Sci, and we're trying to get them as involved as possible, and there's much more to come there. But here's a simple experiment that HAARP I can explain that HAARP does. Again, remember that problem. If I was going to build a transmitting site for 100 hertz, the problem is the wavelength is too long. I can't build a low loss antenna with a useful radiation pattern with a wavelength that's over 300 miles long. I can't do it. And so it's not possible. So I have to use the HAARP site, for example, transmitting it's up to 5 gigawatts HF, 2.6 to 10 megahertz, and put a modulation on our carrier and stimulate the RF at our modulation rate. So the modulation can be anything. It can be FM, it can be chirps, it can be pulses, it can be square waves. And we also scan the beam and paint out half-wave heated regions of the ionosphere to make half-wave radiators in the sky. There's all kinds of good experimentation going. But in this case, they were using a 20 kilohertz modulation of some sort. It just shows how we can power beam into what we call the auroral electrojet. We can modulate the free electrons and stimulate RF, useful, coherent, stable RF at our modulation rate. And that's what we're showing here. So why do we want this low frequency RF? Why is that so interesting? Well, it's interesting because the skin depth, the penetration depth of soil and salt water is kilometers deep at these low RF frequencies. And so if we can get a useful, reliable source of enough low frequency RF from this technique, we can build lossy receivers with negative gain receiving antennas on aircraft or RPVs. We can overfly an area, get the incident wave and the reflected wave, and we can map like an MRI. We can map what's underground, caves, tunnels, bunkers, complexes, natural resources, oil, gas, plate tectonic physics. We can map what's underground to kilometers deep. We can communicate underground. We can communicate to submerged subs. We can map the ocean floor. We can map and find stationary subs that don't make an anomaly. So anyway, but you got to have the low frequency RF first. And that's what HAARP is trying to figure out all the physics for, using the stimulated secondary emission technique, and they're really getting a handle on it. Okay, so now here's an interesting example. HAARP is so good at generating this ULF and ELF through this stimulated secondary emission technique that we got a sound card program, and the bottom one is the easiest one to see, where we transmitted 2 tones, sometimes simultaneously, and we received the low frequency RF. This was down probably under 10 kilohertz as an RF frequency, and let's see, and this is the modulation. No, this is the operating frequency here. Yeah, so we're down at 2 kilohertz to about 5.5. So we were generating RF from about 2 kilohertz to 5.5 kilohertz of RF with these tones. So this tone comes up, another comes another one. So we sent these tones generating RF to spell out HAARP, HAARP. And this was received at a diagnostic building about 90 miles away in Alaska. Very easy and very fun little demonstration of low frequency radio waves. Okay, want to breeze through this. There's a mining school up in Delta Junction, Alaska, halfway to Fairbanks. All they do is move rock. It's just to teach people how to mine professionally. So we use that as a target of opportunity. And so we send our pulsed RF, we generate ULF, ELF, and VLF radio waves. And then we had hand carried receivers. We walked over top of the hill here and we imaged the mine shaft, and we went into the mine shaft and measured how much RF was penetrating and so on. And this was done with only 60 megawatts of ERP, this data, when we didn't have the full array. So you can see that by walking hand-emplaced sensors over this mine tunnel about 100 miles north of us, we were able to get enough reflection and ranging data with some signal processing to image that tunnel underneath of us. It's much better now, but this is just a useful experimental example of using stimulated low frequency RF using high power HF out of the ionosphere and using that for a ground penetrating radar, and it works very well. Okay, this is we're going to wrap it up here in just a second. I see I'm going way long. This is a spot, we just pointed the HAARP beam and a CW carrier up into a night sky, just to let it stimulate artificial air glow or artificial light, artificial aurora, if you will, in that part of the ionosphere. The radiation pattern is widening out as you go. I could not see this with my bare eyes. This is a high sensitivity CCD camera, but it does show what the structure of the ionosphere looks like from just a high power carrier, just a CW no modulation carrier pointed up in the sky. And this is HAARP just causing artificial aurora using a high sensitivity camera to see it. Very easy. Okay, here's just a quick example of some experiments that HAARP does. We can create what are called wave ducts. That's another propagation anomaly we can easily create. We can create distortion or scintillation in satellite signals, especially GPS. We can create GPS distortion on demand. We don't have to wait for nature to do it for us. And then the GPS folks will try algorithms to take the distortion back out to make it more robust. But this is just a way that we can distort paths from satellites. And we can also create what are called field-aligned irregularities, where just by transmitting a carrier, we can create a structure in the ionosphere, which works as a very efficient VHF reflecting mirror. And so we worked with the hams years ago in the Anchorage area, where on 2 meters, they beamed up 200 miles away over the HAARP site, and they had receivers 200 miles south of them on the Kenai Peninsula, and without HAARP transmitting, they heard nothing. But as soon as HAARP started transmitting a carrier, we created the FAI, and suddenly they're getting very strong signals reflected back 200 miles behind them because of this FAI. And then as soon as HAARP stops, it goes away. So again, this is typical experimentation at HAARP, filling the physics journals of radio science. Now, just a quick look. We're in the town of Gakona, Alaska. Beautiful, very rural area. Only one FM station and one AM station in the whole area. But here is the sign, welcome to historic Gakona. And that's pointing at the bar, the Trapper's Den bar, where we spent a lot of good times in that bar with meals and drinking and celebrating and commiserating and meeting all the locals. Great bar. Whoops. So here's another look at the Trapper's Den, our local watering hole that we spent so much time in. They do have pool tables, and it's just a great place. And then here I am on what's called a fish wheel. I wanted to share very quickly a little bit of Alaska with you. A lot of people in Alaska like to live on subsistence. Food is very expensive up there because most of it's imported. And so people like to pull salmon out and they smoke it, they can it. It's like their hamburger is salmon in Alaska. So the people that are residents of the state are allowed to use these homemade devices called a fish wheel. If you're a tourist, you're not supposed to use one. You're supposed to use salmon roe in a bag and a weight and a fishing rod, which does work slowly. But to get fish for your own consumption, you're allowed to use licensed and approved fish wheels that are homemade. And this is a fish wheel near the site. One of our maintenance techs built this, and the whole community shares it to get subsistence fish. And what it is, there's a steel cable on both sides. It's on two floats, and it's permanently positioned on the shore of the Copper River. It never moves. And it has this frame structure here, and it has two chicken wire baskets, and orthogonally 90 degrees, two paddles. And you pull the pin, and the current of the water just starts turning it by just the current of the water. And it grabs a paddle, grabs a basket, grabs the next paddle, grabs the basket. And the salmon, when they run, they come up the sides of the river, never the center. They always come up the shallow sides. So the fish just swim into a basket when it's scooping down, and when the basket hurtles its way up top, there's a chute, and the salmon falls into this little chute that's behind me when it's up vertical, and it shoots the salmon right into this box, and they're just stacked in there like firewood. It's impressive. So there I am, a little bit younger, holding up a salmon I just pulled out of the box. That's called a fish wheel for people that live in Alaska to get subsistence fish in quantity to live on. Okay, let's see here. My computer's deciding not to, whoops, there we are. Okay. So now this is the Alaska pipeline. It's about 14 miles from the site. It's useless to us. It's only carrying crude oil, but it is interesting in that they're using that same thermosiphon technology, although they use ammonia gas. We didn't want to deal with that. And so they're using ammonia gas, but same concept, pulling the heat out in the wintertime, nothing in the summer, to freeze into the stable permafrost crust. But here's the 4-foot diameter insulated Alaska pipeline carrying heated crude down to Valdez. And notice how it's on a sled here because of the earthquake, and also temperature changes are so extreme. They want the pipeline to expand and contract, so they have to be mounted on a sled here to support that movement. But we can't use any of that because it's all crude oil heading for Valdez. Okay, and let's see here. Something on my computer is not one. Okay, there we go. Got to get that fixed. Okay, so here's a view. Whoops, yeah, okay, here's a view of the HAARP array from standing outside the operations center, a third of the mile away. Look at the scale here. The hoarfrost does not bother us, but look at the scale of the array. I still can't get it all in the same picture. And here's a picture of the frosted up array in the middle of the winter time. Again, you can see the ground screen 15 feet up. You can see the guys, you can see the matching units, the even mode loads we talked about, the shelter buildings. There's a maintenance truck out there working on a transmitter in a building. And that's what the HAARP site looks like. And these are 85-foot towers, fat bow ties at the top for low band, 3 wires shorted, reached half dipole for the high band lower down, staying a quarter wave off our ground screen to get maximum energy vertically up. The design space of the HAARP array is to beam vertical and plus or minus 30 degrees in a cone from vertical. That's our official design space. We do push the pattern much lower, whatever the scientists want, and we just handle the higher SWR. And so we do operate beyond that. But that's a quick look at the HAARP site. I took way too much time. So that's what I have. If you want to take the screen back, we can do a little Q&A if you like. And I hope that was understandable. So 7.3 from the HAARP amateur radio station KL7, effective radiated power. Again, a ham club is at the HAARP site, and all visiting scientists and engineers are welcome to use it. Okay, there I am. Does anybody else have any questions? I know I'm not getting any audio right now.
Any questions they want to ask Steve? All right, here's one question for you, Steve. I hope you can hear him.
I can hear
I
you.
saw, can you hear me?
Yes.
I saw on one of your slides something about particle interactions in the atmosphere. Are you aware of any technology relating to this site of a way of getting particles to different layers in the atmosphere or coaxing them out, even maybe as low as the troposphere?
I am not aware of any work in that area. Now, I'm an electrical engineer, not a plasma physicist. So there may be work going on in this area, but I'm not aware of it, and I'm not aware of any of this going on at the HAARP site.
Okay, thank you.
That was a cool question. Anybody else have any questions for Steve? Anybody? Oh, look, they know everything now, Steve.
Well, I don't think I've had this few of questions.
I know, right? Oh, we got one. There you go.
Have you had any problems with wildlife at the site?
Okay, that's a great question. Well, I'm going to answer that in two quick ways. The site has never, through RF, killed any birds to our knowledge. Now, this was a big area of concern, and before it got handed off to UAF, all those years of operations, the government did a huge study, and we mapped every single bird kill, and we never killed any wildlife with the RF at all. Nothing. The only thing we found was that birds were occasionally flying into our guy wires, and we do have bird balls, and we added more bird balls. So no hazard there. Now, as far as wildlife danger to us, the HAARP site does have grizzly bears, black bears, moose, and fox that we would see, and rabbits all the time. So if you're out taking a walk around the HAARP site in the middle of a summer day when it's 70 degrees, you have to always be prepared to be challenged by a black bear or a grizzly bear. Typically, moose won't attack you, but the bears could. So, and through our motion activated cameras on the various science pads, we see that wildlife coming through all the time. So there is a lot of wildlife up there, but we've never had anybody hurt, thankfully.
Okay, I got another question for you.
Hey, Steve, this is Whiskey 8 Charlie India. Michael, how you doing?
Hi, Michael. Good to hear you.
Hey, yeah, I really wanted to thank you for doing this. And the club probably doesn't know, it was, he just accepted to do this about a week and a half or so ago. So really interesting, lots of great story. He's got a whole lot more stories that I won't ask you to repeat them here, but thank you again, man.
All right, thanks for doing this again, short notice for us, Steve. Anybody? Oh, there's another question. Let me make my way around the block. All right. Here you go.
Hi, I'm Chester K8NYC, and I run an EMD locomotive, which is a much smaller motor than what you're using. But I visited the Green Bank Telescope, and they allow only diesel-powered vehicles there. Do you have such a restriction at your site?
Okay, that's an interesting question. The answer is no. There is no restriction, and here's the reason. The Green Bank facility obviously is a radio science receiving site where it's all about receiving, obviously very weak signals there. And they're also in a quiet zone where there's been a determined effort through FCC licensing to keep major RF signal generators, geographically away from that area to reduce noise floor. We, however, are kind of not dominantly, but we're significantly a transmitting site. We have many, many, many different transmitters, and we do have a lot of receivers at the site, but most of our receivers are at remote locations that are up to 30 to 40 miles away typically. So we have internet connected remote receiver sites around Alaska that are in quieter areas. But since we're fundamentally a transmitting site, any noise from ignition type cars would be insignificant to us.
All right, thank you. Anybody? Oh, there's another question. Sure, I walked away.
Hey, you do that thing where you think a question and then somebody hands you a mic and you forget it. Yeah, I'm doing that right now. But anyways, essentially, oh yeah, do you guys have a repository for any of the underground data that you're able to pull off of that?
Well, I'm sure there is. HAARP doesn't necessarily maintain an accessible depository. The way the HAARP site works, and this will be an interesting way to answer your question. So the HAARP site, has this DC to light capability, and we have this big HF transmitting site for the ionospheric, modification and study work. But when HAARP runs a campaign, what we typically do is we look over the experiments, and we usually handle anywhere from 3 to 6 unrelated experimenters through a 2 to 3 week campaign. And we interleave them. Like, let's say we had 3 experimenters for 3 weeks, and they're completely unrelated to one another, completely different areas of science, radio science. So we would give, on each hour, we would give one guy the first 20 minutes. And then for the second 20 minutes, we give the second guy his time. And for the third 20 minutes, we give that guy his time. And they could be wildly different. One could be communications, one could be deep space, one could be ULF generation, just completely unrelated. They're just interleaved in time to give people access. So the amount of data that we collect hour after hour, day after day, for up to 6 scientists per hour, is just massive. So what our job is to collect that data and to get it to the experimenter for them to take home. And then they take that data from our receiver sites, from the transmitters, from whatever their diagnostics are, and they take all that data and they go figure out what their success or failure was, and they go then, keep record of it. So we're kind of the middleman, not keeping tons of records. We just provide the service.
Okay, thank you very much.
That was very interesting. I never thought of it that way. Anybody else have any questions? Anyone? Logan, was there any online? Hang on.
By the way, while we're looking, I wanted to tell you folks that I've been coming to the Dayton Hamvention every year, really for the past 25 years. And when I was younger and didn't have as much money, I'd come every 3 to 5 years. It is one of the highlight events of my year. So many friends, so much to learn, and it's such a positive, well-run event that I just wanted to thank the Dayton Amateur Radio Association for doing such a great job with all those volunteers. It's just fantastic, and I have so much fun, and it's the highlight of my year. So thank you.
Has he ordered his ticket yet?
Have you ordered your ticket yet?
You know what? I don't think I have, and I'm going to order it momentarily. I always
Great.
get it early.
So Robert wants to know, can visitors go visit HAARP and take a tour?
Okay, that's a great question. So here's the answer. HAARP holds an official open house that anybody can come to about every 2 years. And it's typically for 1 day in the month of August. And they usually announce it, and people will travel up there and come to the site that day. And they have scientists, showing test data and showing their work. And we have transmitters running into dummy loads and opened up. And it's a big, big tour. But that's only 1 day every 2 years. So the way it's been going is that if somebody knows me and reaches out to me with enough advance notice, I can easily set up a tour of the site. If you're going to be in Alaska, and there's a beautiful B&B just 7 miles away that's just gorgeous. But so it's a beautiful part of the state, very remote. But if somebody contacts me and gives me 2 to 3 months advance notice, I can set up a tour, and we do that for hams and broadcast engineers routinely. So it's
Great.
so,
Do you guys have any association with SETI? SETI?
yeah, I'm aware of SETI, and the answer is fundamentally no.
Is that all the questions?
The one thing we do with SETI is at times they will partner with us and provide a high sensitivity receiver system to us, planned well ahead of time, to aid in some experiments that are going on, but that's very intermittent involvement, and that's about as far as it goes.
All right, that's all the ones watching online that had questions. I don't think anybody else in the room has a question. No? Steve, I want to thank you very much for your time, and I appreciate all the info, and you're a wonderful speaker. Thank you.
Okay, well, I hope that was reasonably well presented. It's so much information to get through in so little time, but I hope you enjoyed it. And the site is very active, and it's very reliable, and the science is just pouring out of that place, and it's fun to watch. So thank you very much for inviting me, and thank you again for all of your work with the Dayton Hamvention. It is one of the highlights of my year, every year.